Hi and welcome to week 7 of Maya Bifrost training. This week we're going to be having a look at how to paint Bifrost attributes onto accelerator meshes, and we're also going to be having a look at how to set up Maya Bifrost droplets. We're also going to have an in-depth look at how to simulate and mesh Bifrost simulations and how the lighting and surfacing takes place and all the different settings that you need to have set onto your shader to get a really nice rendered water surface. So let's get started. To get started in this scene, I'm going to load in the Deep Ocean Maya Bifrost example out of the Maya Bifrost examples directory. And what that basically has is a Bifrost simulation of an ocean with a wave mesh on the top that animates, that drives the underlying particle movement through Bifrost acceleration. Animated Bifrost accelerator mesh, which is moving like an ocean surface. And what we're going to do is right click, select the mesh with the left click, then right click in an open part of the viewport away from the mesh. And what you'll see is that you can go down to Bifrost, Paint Accelerator Influence. What this allows you to do is create a large or small paintbrush and be able to paint the accelerator influence across the surface of the Bifrost accelerator mesh. And what this enables you to do is effectively use only one part of the mesh to enable acceleration. Now, this has the advantage of being able to have accelerator meshes that may not need to be active in a certain part of your scene. So what you really want to do is paint black in the area where you don't want the accelerator to influence the particles, and white in the area where you do want it to influence the particles. So if we enable our Bifrost liquid now and run a simulation, what we'll see is that the Bifrost accelerator mesh now won't affect the whole Bifrost particle area. It will only affect the right hand side, and the left hand side won't be affected. So this is background processing at the moment. We'll just pause the video and restart it when it's finished. And what you'll see here is when we scrub through the timeline and just hide that mesh, we'll see that the acceleration is happening on the right, but it's not happening on the left because we've painted the attribute to be 0 on the left. So one thing to note is as you're painting, you can hit the B key to scale up or down the size of the brush, and you can hit Control to switch between painting black or white. So it's a very easy process, and it makes for some interesting effects that you can use maybe in beach scenes or around the wake of ships and things like this, where you want accelerators to affect the object, but you don't want to have it affect the whole particle simulation. You want it more localized around a certain area. So this is a good way to generate waves at one side of a pond, or effects that only happen in one area. But apart from that, I'm not sure what this kind of effect would be useful for, but it's handy that it's there regardless. So the other thing I'll show you is once that accelerator mesh is visible, it's just a matter of right-clicking not on the mesh but in a clear part of the scene and scrolling down to Bifrost, Paint Accelerator Influence. So just make sure that that's the way that you do that to get painting attributes happening. Next thing we're going to have a rundown of is Bifrost droplet settings. Now, Bifrost droplets are very straightforward and not very complicated procedure, and whereas the rendering and meshing and shaders of Bifrost liquids is extremely complicated and very difficult, and there's lots of settings that will break it. So we're going to cover that in great detail and just run quickly over the droplets now, so that you can see what it means. Now, the word droplet is a little bit misleading because it makes it sound as if we're talking about the spray that comes off Bifrost fluids. That actually isn't what it is. It's actually just an optimization code that is written into the Bifrost software, which enables you to skip a few CPU cycles when you're running sims. So Bifrost droplets are basically splitting off particles that fly into the air and calculating them just as regular particles instead of as liquid simulation particles. So the difference between a liquid simulation and a normal particle simulation is the particles intercollide, they stick to each other, and all kinds of different complex per particle events like that. So we've just added a few keyframes in here of the collider object that's coming into the water. Now it's important to note that the droplet threshold, which goes from 0 to 1, it's important to know what you're actually setting with it. So 0 is going to create almost all the particles that disconnect from the main liquid into droplets, and 1 is going to create no droplets. So if you set it to, say, 0.4, then that will be a lot of droplets and but still some liquid particles, whereas if you set it to 1, there's going to be no droplets at all. So it's important to explain what these droplets actually are. They're actually just particles that are calculated in a more mathematically simple way. So you can see here that the spray that comes off this splash, all the particles that are flying out from the main center of the splash, some of them are droplets. You can actually see which ones are droplets and which ones are liquid simulation particles, or which percentage have been converted to droplets by using the drop-down menu in the color channel setting. So if we change the color channel to droplet, you'll see that the light blue particles are the droplet particles, and the dark blue particles are the liquid simulation particles. So there's quite a significant CPU and memory sort of decrease that occurs from using droplets, because you're not having to calculate every single particle as a full-blown liquid simulation. The downside is that they kind of just fly off like spray, and they don't keep the water shape that you would get from real water particles. So you don't get the sort of scientific accuracy of a real water spray. But in some circumstances, like if you're running a dinosaur down a creek or something like that, you may not want the extra time that it takes to generate. So what I'm going to do now is set the droplet threshold to 1, which will eliminate all droplets from the scene. And using the magic of television, we're going to re-simulate this and pause the video, and then when it comes back, you'll see that the colliding object will hit through this water, and it will create a an impact that will have no droplets in it. Now the difference between these two simulations is that in the same time I've been able to simulate twice as much of the droplet enabled simulation as the droplet disabled simulation. So this simulation looks a lot more natural. It's got a much more liquid looking shapes and energy flow of force through the particles. And you can see here, as we change it to the color channel to droplet, you can see that there's 0 droplets in this simulation. So no airborne particles have been converted to droplets for calculations. Now, this is really going to be a shot by shot choice. There's no one setting that works for every single shot. It's really up to you as to whether or not you need, you need to enable this setting or not. But it's definitely a really great feature that enables you to save a ton of time, and it reduces the memory overhead and the CPU overhead of running Bifrost simulations. Alright, now that we've covered droplets, we're going to be looking at droplets and rendering the meshing, lighting, shading, and the materials of this helicopter crash sequence. So if you've got, one thing to note, if you've got a super fast computer, you'll be able to put in higher mesh settings than I've used in this scene, because I'm trying to cater for everyone. But I'll give you extra high settings that you can enable in your scene so that you're able to get more detailed meshing. This is quite a large simulation. There's like 20 billion particles or something along those lines in this sim, and when it's meshed, you'll lose a little bit of detail in the simulation. But I'm sure in future versions of rendering engines, you're going to get some really amazing underwater shaders happening that will pick up the under the surface liquid simulations. So we can see with this simulation, there's just a tremendous amount of detail in the motion of the fluid. Not so much as the helicopter crashes, but more in the movement of the waves and the underwater turbulence that's occurring with the particles. I mean, that's just a tremendous amount of detail to get out of a liquid simulation. That would have been taken a really long time in years gone by to simulate that kind of thing on really high-end computers. And now you can easily do this kind of simulation on a laptop. No worries at all. Meshing it is another story. You won't be able to mesh this at the same detail that the particles are simmed at, primarily because of the limitations of your GPU and your CPU. So just be advised that even if you get a spectacular particle sim, you may not be able to mesh it on your machine quite the same way as you, at the same level of detail as you can sim it. So to get this scene started, we're going to roll in helicopter crash version 201 or version 101. It doesn't really matter. They're both the same, similar scene. And what this will be is the original file that we've worked with in a previous exercise to study collision objects. So the Bifrost liquid, we're going to be changing the settings of this to get a much more detailed ocean kind of scale simulation. So before we were using a master voxel size of 0.2. Now we're going to use a master voxel size of 0.06. And what that's going to allow us to do is get a much larger scale looking liquid simulation. Once you've set the master voxel size to 0.06, we're going to cache this simulation to disk straight away. The reason you don't use scratch caching on these large simulations is because a typical computer will have about, a laptop will have 8 gig of RAM, and a PC might have up to about 16 or 32 gig of RAM. But these kind of simulations, the cache folder for it is nearly 200 gig. So that's just too much RAM to have on a normal computer in this sort of time frame. So the reason you cache it to disk is because each frame of this fluid simulation cache at this master voxel size is going to be about 250 to 300 megabytes per frame. So what we're going to want to do is keep the keep the setting and the detail really high, and not worry about interactive RAM-based scratch caching, and just cache it straight to disk. So you must have enable background processing turned off, enable scratch caching turned off. I've overridden the disk location, and you can also set it on the Bifrost liquid as well to be in a new folder. Make sure the scratch cache is flushed. The reason we do this is because you don't want it background processing and caching the disk at the same time, which it will do if you don't have the settings correct. So once you've got the got those all disabled, you can select the Bifrost fluid and press compute and cache to disk. So that's your cache directory at the top. That'll be where the cache files per frame are going to be set. That's the cache name. So I'm just going to change this now to my own custom directory, and I've already simulated mine, but this will probably take 12 hours or 5 hours depending on what CPU and RAM configuration you have and how fast your disk is. But I simulated this overnight, and it was finished the next day. So I've got start frame -50 for some pre-roll and end frame 290. So that's quite a lot of frames of simulation. But we'll check out how that looks anyway. So once that's been simulated, you'll have a disk cached water simulation, and it's going to be finished, but you're not going to be able to just scrub the timeline because every frame is around 250 megabytes of data that has to read into the package. So if we just go to frame 79, just picking a specific frame in this little window down here is the best way to move to certain frames, and you can see the time it takes just to load that one frame into the scene. So I'm just going to pause here, and then I'll show you what that looks like. So at frame 79, this is what the simulation looks like. So we've got a really large amount of detail in that water, where the particles interact with the surface of the ocean, where the helicopter crashes in. There's a large splash that's come up from the surface, and there's just a great amount of turbulent detail of particle movement on this fluid surface. So when you see this detail, this is really what you're going to be able to render soon using custom shaders that will transparently render this liquid surface. But for the time being, the meshing and shaders of Bifrost is pretty straightforward and pretty basic, and you lose a lot of detail by wrapping geometry around this spray because it's so detailed. Like every single droplet of this water needs to be a triangulated polygon mesh, and that's just a lot of detail to hold into a computer. So what I'm going to do is run a play blast now so that I can see what my simulation looks like, and that's the workflow for viewing your simulation that you've already cached to disk. So the process is, for big simulations, cache to disk, load it up in the scene, and then play blast the scene so that you can see what the simulation looks like. And that can take a couple of hours just to play blast that scene in your computer, because each frame has to load the 250 meg particle cache into memory so that it can load back the water simulation and see what it looks like. So with this play blast, that's just loading into RAM now, and we can see that there's just a tremendous amount of detail, not so much in the crash of the helicopter, but in the actual wave movement and the spray that comes off the waves themselves. So from looking at this simulation, you can see that there's a tremendous amount of detail that that's coming out of it, and you can sort of see the scale of this simulation. So I mean, the helicopter is probably a little bit small in this size, but at this setting, 0.06, you can see that the waves look like they would be, a person would about 6 foot would stand in those waves, and you can imagine that this is just at the beach down at the Gold Coast or Sunshine Coast or something like that. And if you're from overseas, it would be, like a coastal beach break. But you can definitely clearly see the scale and realism of that water simulation without any problems. So what is a good idea is to keep these settings and then scale your vehicles or interacting surfaces to match up with this scale of Bifrost liquid. So on the color channel now, we are showing the droplets. So we were learning about droplets earlier in the lesson, and this is the droplets from this Bifrost simulation. So we can see here that a lot of the spray particles that have come up off the top of this are being calculated as droplet particles, and then when they fall back into the liquid simulation, they will rejoin back to the liquid, be liquid particles. But those light blue droplets are the droplet simulated particles, and the dark blue particles are the liquid simulated particles. So changing the droplet setting will allow you to increase or decrease those particle amounts, less or more droplets. And the threshold, if you say did 0.2, you'd get a lot of droplets, and if you set it to 1, you'd get no droplets. So that's really up to you, up to your own artistic ideas, but that's basically the what it looks like. If we drop the color channel down to vorticity, we can see which particles are above the threshold for that setting. So vorticity is important to have a look at in the color channel drop down list, because that is one of the settings that affects the rendering of the liquid. So the velocity also affects it, but it's a mixture of the vorticity and the velocity combined together that creates the shader properties for that liquid. So have a look at the color channel drop downs, and you'll be able to see the different attributes displayed as color ramps with the with that drop down setting. So that's really good when you're wanting to test and see, why isn't my render working, or why can't I see something a certain way. That'll give you a good indication of what's going on, and troubleshoot the simulation or the render shader settings to see what's happening. So I'm just going to set another frame now, 120, and I'm just going to show you now the cache file size, so that I can give you a better understanding of why we're discaching and we're not doing a lot of timeline scrubbing and things like that. We can see here the for this big simulation, there's each water cache BIF file is 297 megabytes, and these ones are other sizes ranging from 250 to 310, and the folder is 148 gigabytes. So that's really large. That's as large as some external hard drives are. So just to give you an awareness of how much data you're generating from these water simulations, it's really just a massive amount of data. It's just extremely large just for one shot, and one component of one shot is 148 gigs of data, even before you've rendered it. That's just the particle simulation. So what we're trying to highlight here is that the particle data takes up that much data, then the mesh takes up more data per frame, probably more than the particle data. And then the rendered frames take up footage as well, especially if you do several passes. So you have to really be cautious about your data management for these kind of Bifrost simulations. And if you're working on a TV series or TV commercials, you just really need to be cautious of how you're using disk space on the server, because this can really blow out and fill up your server really quickly. So we're going to start setting up the render settings for this simulation now. So I've just set the resolution in the render settings dialog box to be 1440 by 900, and I'm going to load in a image-based lighting HDR sphere to light this scene. So with rendering water, it's important that you have the color underneath the water, especially if it's thin, that matches the color you want the water to be. For example, you wouldn't put, a beach underwater that you want to look really deep blue colored. You're going to have to put a sort of blue sky kind of colored surface underneath the water so that it's able to reflect and refract that kind of color underneath the ocean. So all you have to do is download a HDR off the internet, and there's thousands of free HDRs you can get from different websites that you can easily search through Google, and it's basically just a spherically mapped wraparound scene that's bright in certain areas and dark in other areas, and that will actually light, reflect, and basically just render really nicely water and surfaces like that with the correct reflection, and it won't tile or anything like that. It'll just give you a really nice look for your scene. HDR images are becoming more prevalent in lighting. They're starting to abandon the traditional spotlight, direct light sort of system for lighting in shows like Transformers and Iron Man and Avengers and things like that. They're opting more for a HDR based workflow, and that is basically image based lighting rather than spotlights and directional lights. So that's what we're going to use in here. You can load in any HDR you like for this example, doesn't matter. And what we're going to do next is we're going to load on the mesh for this scene so that you can see the mesh from Bifrost wrapped over the particles. So if we select meshing enable off in the settings, that will enable us to change the settings without it constantly updating the scene, which can take about 2 to 10 minutes in this large scale sim. So one of the things that's really important to do is these settings in the meshing settings are really important, and they drastically affect the look of the mesh. So you could be loading in a really detailed sim and it can get a really low detail mesh. Basically the meshing resolution factor of 2 will give you a pretty good mesh that matches your particle simulation. However, if you're using a laptop or a lower end computer, it's not actually going to be able to have enough CPU horsepower or RAM or disk space to actually hold the billions of polygons that are going to be generated in that mesh. So what you actually have to do is just use lower settings, like a setting of 1 in that detail setting, and then that will work a lot easier. So what I've done now is just loaded up a scene that has this tropical beach HDR background image. I have put my settings on for my mesh, and on the mesh itself is assigned the Bifrost liquid shader. And the reason why I'm using this tropical beach environment is because it has a blue color to it, and so my water is going to render out blue in its refraction and its reflection. So if I now load up the Bifrost, you can see here the Bifrost liquid itself is hidden. That's very important, because if you have the mesh and the liquid both visible, it's going to render the voxel surface and the mesh together in Metal Ray, and that's just going to take up too much memory and waste a ton of time, and it won't look correct. So you have to actually hide the Bifrost liquid and have the Bifrost mesh visible by itself. So we can see the mesh here. It's very, very detailed, very densely tessellated surface. Some of the settings on this aren't 100% perfect, but for the time being, this will give us a good indicator and a good starting point for our liquid material that we're going to adjust. We can see the background pretty clearly through this. It's just a gradient of blue and sand colored water. Now, by default, the material that is assigned to this water will be incorrect. It'll actually be the ramp shader material, which is right there. So when you load in this scene, your water will actually look like this. And now, even though it looks good in the GPU in the viewport, that's actually the water shader, which is just meant to be used to visualize your water and see how it's kind of looking. The main shader that you'll be using is the Bifrost fluid shader, and when you assign that, it'll actually look totally clear, and you won't be able to see any color on the surface, because it's totally transparent and it doesn't have as much color as that ramp material. So if we jump into the Hypershade and load this Bifrost liquid, make sure you have the mesh selected. Now, this is a pretty tricky shader. The rendered look of it isn't really indicative of how the actual liquid itself will look. So this rendered template can look totally wrong, but the liquid will look totally correct. So it's a very complex shader, and for that reason, I've got the help file copied into this PDF for this liquid shader, so that you can see all the parameters and the settings for each value in this shader, because they really don't exist anywhere else in Maya, and understanding other shaders in Maya won't help you understand this shader a lot. So the main thing that you need to understand is that the remapping of these reflection, foam, refraction, and other settings like that are tightly linked to the vorticity and velocity of the particle simulation. So the vorticity and velocity is set to certain minimum and maximum settings, and if you don't have those exactly set correctly to your shader, they will render totally incorrectly. So what I've got in here is the correct value for foam remapping is 0.02 or 0.08 or something like that, because if you have it any higher, the foam becomes more like iridescent white out kind of liquid paper instead of foam. And the foam is such a great setting. I mean, I remember rendering real flow simulations that were supposed to be tornadoes or things like that, and it was just so amazing to be able to have this foam as part of the liquid simulation, because you don't always have a totally flat, glass of water. Sometimes you've got like a foamy tornado or different effect that you need to get working. So I've disabled the refraction and reflection weight remapping because we don't want to have that wrongly set to break the shader, and that's your velocity and your vorticity scale down the bottom there, and that's your diffuse color remapping. So once that's set up, you want to get the highest mesh detail you can out of your computer, and there's some other great settings on Igor Effects, which is his one of the Bifrost developers. And if we go to a certain frame, this is frame 92, and we render that, that's what our foam settings will look like. So I had the settings set correctly. You can check the video if you need to have a look at them again. But that's what it looks like rendered with a detail level of 1 for the Bifrost mesh, and the foam refraction reflection settings set as they are in the settings. So I'll just show you what happens if you increase the foam remapping value. So now I've got it set to 0.5 in that ramp, and if we render half of this water, what you'll actually see is that will create a really white looking foam area where it's rendering the velocity and vorticity. So for me, the render on the left looks best, but the render on the right has got really extreme kind of like surf foam happening in there, and it's really up to you what look you're looking for. You can easily render out black and white and then comp it over the top as an additive later and reduce it. But I think it's best to just get the shader really, really nice in one pass of rendering. They're starting to move away from the 65 rendered layers comped together and drastically adjusted kind of effect with graphics now. They're just getting everything really nice in one layer and then like breaking it out into different layers to adjust it for the compositor. So it's best to just get the settings correct in the shader itself rather than messing around with it in comp. But yeah, that's the settings that work nicely for that shader. So I've just disabled reflection and refraction remapping. I've got the foam remapping enabled, and at 1 its selected value is 0.08, and that gives a good look for this specific scene that we're working on. So with these directional and point lights, because I've got a HDR in this image, they're not really desperately necessary, because the lighting and the reflection and refraction is coming from the actual image itself, and I wouldn't advise using global illumination and all kinds of ambient occlusion and things like this for these kind of extremely high detailed geometry scenes. I mean, that's really ideal for architectural visualization and hard surface reflective objects and things like that, but it's better not to use it for these kind of detail level of geometry because it will just break the computer. So whatever background image you want to use, just showing you here the depending on what you're using, it's better to use a less specific descript image for the background HDR image, because if you have like a house or a tree or something like right in the middle of the background, that's going to show through your water and reflect in your sky. So you really just want to use a nondescript kind of colored shaded background for this kind of water rendering, then you'll get a much more consistent, less frustrating result. It's a little bit difficult to see the water surface, but if you look at the highlights there, you can see where the geometry is being generated. And unlike RealFlow, instead of generating, you actually simulate create the geometry per frame and it saves it in there. This actually will just generate it per frame, like as you're working, which I think is good because it saves a lot of disk space, not having to create a 600 megabyte per frame geometry caches. So another feature of this meshing that's really great, and I highly recommend using it, is this feature where you're able to create a clipping area. So what you can do is you create a simple shape like this polygon cube, and its geometry out plugs into the Bifrost mesh clipping in, and creates a clipping area where the mesh won't be generated outside of that geometry. So the Bifrost shape here is the one that you need to use it in the node editor. So all you need to do to link them together is attach the p-cube shape mesh out to the Bifrost shape mesh clipping in. And just on this side, if you go down to out mesh, select that and plug it into other, and then in Bifrost it'll have a highlighted setting called mesh clip input mesh. And once that's linked together, the Bifrost mesh will only generate inside the polygon cube that you've modeled, which is really good for testing your scene. And once you don't want to use that anymore, you can just delete it or unlink it. So we can see here that inside the polygon cube that we've modeled is the only place that that water mesh is being generated, and it's really just a great great method for testing your meshing. It's a bit like region rendering, so you just want to check a small section of your render. This is a great way to experiment with different settings of the mesh without having to wait for 10 minutes for it to remesh the whole large water simulation, especially with things like droplet radius and surface radius and things like that you really just don't want to wait for 10 years to see the effects of, and smoothing and all kinds of settings like that. It's just a great feature for sort of region meshing your simulations. Just make sure you don't move the geometry around the place, because what'll happen is it'll recalculate the mesh every time you move it. You just have to disable the mesh and do your scaling and adjustments with the mesh disabled, and then re-enable it again. Otherwise you'll be waiting forever every time you translate that polygon cube or polygon surface that you're using. So hopefully that helps you generate your meshes. Feel free to set your meshes to mesh resolution 2 to get more detailed settings for your simulation that you guys are running. And if you're running on a laptop or a computer with 8 to 16 gigs of RAM, I definitely wouldn't recommend putting a meshing resolution of that's really high or having high smoothing values in there. The last thing I really want to show you is how to render the straight voxel surface by itself. So just to let you know, a high-end VFX facility like ILM is going to be able to render the particles by themselves without any meshing taking place. The meshing is going to actually take place in RenderMan or in Arnold or in another renderer, just using the particles that you've generated. And amazingly, Bifrost already enables us to do this using the voxel surface. So if you actually make the voxel surface visible and load up the just the particles and hide the mesh, you'll actually be able to render out the voxels to give you a liquid surface that looks like the meshed object. Meshing is a good idea to kind of avoid that stage if possible. And as that voxel meshing becomes more advanced and more settings get added to it, I definitely would recommend using the voxel surface to mesh the particles rather than that extra step of meshing the liquid. Well, thanks very much for listening to this week's lesson. I hope it was really helpful. If you have any questions about the material or the particle simulation procedures, make sure to post your questions onto the forum.